Hello and thank you for watching my video. My name is Astrid Krasniqi. I'm CCNA and CCNP certified instructor. On this video, we are covering CCNA CyberOps, and this is chapter 4, Network Protocols and Services. This is section 4.2, Ethernet and Internet Protocol, IPv4 and IPv6. This is section 4.2.4, Types of IPv4 Addresses. IPv4 address classes and default subnets. Now in 1981, what they did is they separated the classes into 5 different classes. The whole IP range. IP, remember, is made out of 32 bits, yeah? 32 bits, and this is will generate just about 4.3 billion addresses, right? And they said, okay, well, what we can do, we can separate it on the 5 different classes. So we have class A. 50% of this addresses that we have, they're going to go class A, and big organizations, they will be able to purchase these. And then medium-sized organization, 25%, they'll set them to class B, and then the rest class C and D and E. E was okay for future research. Future research wasn't even used. Medium-sized companies, they could go for class B, and small companies go for class C. And they found out that, okay, well, that didn't really work. You know, because the companies that would come up and wanted to buy an IP address or IP range addresses, and they would say, okay, well, what class do you want? Do you want A, B, or C? Because D was used, for reserved for multicast. You couldn't be selling them. So it was just A, B, or C. And most of the companies, yeah, I'll go for A. And soon, right away, they find out that, okay, well, we're running out of IPv4 addresses, and we have to do something. So what they did is they created this RFC 1918. RFC 1918 said, okay, from this range that we have to reserve some addresses that we can't use them on the internet. And these addresses, they could be used within your company, but they have to be converted to public addresses when they want to go to the internet. So these addresses, they were called private addresses. Anyway, we still use them, still on the network today. We have. So class A networks. So class A networks, they will any address from 0000, that's a class A, up to 127.255.255. That's a class A. 255. I'm not going to write 255 all the time. But this is, we look at the first octet to identify what classes do they belong. This is class A. Then class B, class B starts from 128.0.0.0 and goes all the way to 191.255.255.255. That's class B. And we have class C, there's 192.0.0.0, and this goes all the way to 223.255.255.255.255. That's class C. And then the last one, we have a class D, which is 224.0.0.0. And this goes all the way up to 239.255.255.255. And 240 all the way up to 255 is class E, which is reserved for research. Class D is reserved. This is reserved for multicast. Okay, they saw that, okay, well, this idea of different classes really didn't work. So they said, okay, well, what we need to do, we create RFC 1918. We take a bunch of addresses that are not routable on the internet. They shouldn't be going to the internet. If you need to go, these addresses, for example, say this is a company here and it's picking the address 10. I'm using 10. And there's another company here that can pick the same address. We can reuse them. That's why we still have them IPv4 addresses. But when they go to the internet, say here, internet, they need to be converted. So private address, this is a private address, needs to be converted to public address. And public address has to be unique on the internet. Here, they just, as long as they are unique within the company, it's all good. Some special addresses that we have. For example, first of all, let's go through the RFCs. So RFC 1918, we have that reserved. RFC 1918, so 10 network, 172.16 network, up to, this is a /12, yeah? So 172.16.00, this goes to 172.31.255.255. Then we have a class here for class Here we have 192.168.0.0/16. That's another RFC. So 3 RFCs here. Other reserved addresses that we have is, for example, source hosts on this network. So we can't have that. That's a special address. As well as a loopback address. So 127.0.0/8, the whole class A is being reserved for loopback address. So loopback address, the computers before, they didn't have a network interface card. So once you install the card, you put the driver in. To make sure that everything is working, we would ping. So ping 127.0.0.1. You can ping anything. It doesn't have to be 1. So 127, we usually 0.0.1, but we could ping anything. 127. I don't know. It's a whole thing reserved. So we can ping 1.2.3. Same effect. To make sure that you have installed your network card correctly. Other things that you really need to know is 192.0.2.0. This is a test net. This is reserved for documentation and example codes. So these are not usable. Quite a lot of addresses not usable. 624 relay any cost. Then another important thing is 164.0.0/10. This address is here. These are reserved shared addresses for version 4 and version 6 transition mechanisms. We have, obviously, these are the multicast. 224.0.0.4 is a multicast address. 240, these are for research, for future use. 164.0.0/10. This one, just so you know, this is like a private address. Private, same as the RFC 19, but these are for ISPs. So ISPs, they could be using inside. They are not routable on the internet either. Section 4.2.5, the default gateway. Now, host forwarding decisions. Now, host could be forwarding to itself, communicate with itself. Like I said earlier, when we install the network interface card, making sure that everything is communicate, everything is working, the TCP/IP stack is operating correctly, even if you have so TCP/IP stack, yeah. Even if you have not got the cable connected to that, you still ping 127.0.0.1. You check in yourself, making sure that everything is fine. The network card is fine, the drivers are fine, and so on. The PC could ping this is, for example, if this network is 192.168.1.0, that's our network. Now, if this network, all the PCs on that network, even if a server, it's got the same address, same network address, the PC can communicate. That's a local communication. The PC communicates here. Even the router, the PC communicates. That's called the local host, communicated to another local host on the same network. So do you remember how we found out if it's same network? Well, we use the IP address, and we use a subnet mask, and we do AND operation. So 1 and 1, and 1 and 1 is 1 and everything else was 0, and find out the network address. And then when we trying to ping something, we compare it if it's in our network. If it's on our network, then we compare it directly. If it's not on our network, that's called a remote network. So in remote network, the PC will have to use a default gateway. So it sends a packet to the default gateway, and hopefully the default gateway knows how to get to the destination. And then the destination will reply to the default gateway, and the default gateway will reply to the PC here. So when we give an IP address to the device, we have to make sure that of course, we give an IP address, like for example, 10.0.0.1, we give it a subnet mask, and we give a default gateway. Default gateway is only important if we want this device to actually access a remote device. If we don't want this device or this host or end device to communicate with any remote networks, don't assign this. Then it's going to be confined only on the local network, or be able to communicate only with the local network. So yeah, we go to this local area connection properties using control panel, and then we click here, and then it says properties, and we open here. So we can assign an IP address automatically, obtain an IP address automatically. This will be if you're using DHCP, or you can put it manual. This is manual. If you click here, if you click on that and you can't access the DHCP server, then you will be assigning yourself an APIPA, automatic private IP addressing. So anything with a 169.254 something. That's APIPA. Let me go back. I think it should have been here when we were talking APIPA 169. Yeah, there we go. Link local address. That's APIPA 169.254.00/16. So anything with the 00 after is going to be randomly chosen. Well, first it's going to ping it. Okay. If we want to see what is IP addresses, or what is the routing table of the device, well, then we run the command netstat -r. We'll see what is the active routes, what is IPv4 routing table. This is on the end device, yeah. So the end device, we run netstat -r. For example, this says what is our gateway. Any network, so 0000 means any destination with any subnet mask, we're just going to forward it to the gateway. And that is our interface on the interface, exit interface. Then what we have here, other information that we have here, this is a loopback. If you remember, 127.0.0.0, 127.0.0.1, up to 127.255.255. That's all loopback information, right? So we have a loopback. Then other information is about our network, what network we belong. So we belong in 192.168.10.0. That's our subnet. That's our broadcast address, 192.168.10.255. That's our IP address, 192.168.10.10. Then other information here, have a multicast address. This is used to one-to-many communication, and then our broadcast address. Next section, 4.2.6, IPv6. Now IPv6 is 128 bits. 128 bits is represented in 32 hexadecimal values. Every 4 bit represented by 1 hexadecimal value. These are called hexadets, we're going to see very soon. Now IPv6 is the reason why we move into IPv6 is because pretty much we have run out IPv4 addresses. And you can see here in North America, we have IPv4 has been exhaustion, date of July 2015. Pretty much that we don't have an IPv4 addresses. There's some in African regional internet registries, but the rest is pretty much finished. So we have to move on to IPv6 address. But while we're moving on, there's going to be coexistence. We need to have, for example, be able to transition from IPv4 to IPv6. We have to have both of them working at the same time. There's one type, this is called the dual, if I go back here. This is called the dual stack. In dual stack, a device will work IPv4 and IPv6, has 2 stacks. So dual stack. And dual stack has been around for a long time. Yeah, since Windows XP, we had Service Pack 3, we had dual stack, where the devices have run both. They've run IPv4 and IPv6. Most of the devices these days, they are dual stack. We have a router, a dual stack router that can actually do both. They can tunnel IPv6 addresses. So we do use a tunneling IPv6 addresses. So for example, this router is dual stack router, takes IPv6 and tunnels it inside IPv4. When it goes to the other side opens that tunnel, and it converts it to IPv6 again. Or we can have a translator, NAT, Network Address Translation 624. So this router takes IPv4 addresses and it translates them to IPv6, or it can take IPv6 addresses and translate them to IPv4. So IPv6 addresses representation. This is a full expanded IPv6 address. For example, remember each bit, so it's 128 bits, but it's represented in hexadecimal values. One hexadecimal value, for example, this 2 here, has got 4 bits. Yeah. So we have 4 bits. So we have, remember, 8, 4, 2, and 1. This is conversion table. So 2. Well, 0 and 8, 0 and 4, 1 and 2, and 0 there. That's 2. 0 is 4 zeros, so 1, 2, 3, 4. another 0, so that was 0, 0 there, another 0, 0, 0, 0, 0, that's 0 there, and then 1 was 0, 0, 0, 1. So that is 16 bits. So 4, 8, 12, 16. So one, let me clear this. So one of this is 16 bits. And this is called a hextet. 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 So we need to have 8 hextets. So 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 hextets in IPv6. One hextet is 16 bit. So 16 and 16 is 32, and 16 48, and 16 64. Usually that's our network. And then we have 80, 96, and so on, up to 128. Right. Now IPv6 is quite a lot of numbers and, well, numbers and letters. That's a hexadecimal. What we can do, we can actually compress IPv6 address. So any leading zeros, for example, that's a leading 0 in that hexet. So that's a hexet. So on that hexet, there's a leading 0 there. We can remove that. On that hexet, which is the third hexet, there's 3 leading zeros which we can remove. Not the last one. On that hexet, there's no any leading 0. On this one, there's 3. 1, 2, 3. 1, 2, 3. Here we have 1, 2, 3. So we can remove all leading zeros, and that leaves us with IP address 2001. There was nothing leading zeros there. That 0 we don't need to write. That 0, those 3 zeros, we can just write them as 0. So we can compress the address like that. But we can compress it even further. Any contiguous zeros like this, we can just say double column here. That's compressing it even further. So any leading zeros. So if you have, for example, say 2001, say we have 0 db8, and say we have 0001, say we have 0A00, right? These are zeros. And then let me just write, that's 64, yeah? The network. So there is no leading zeros here. So with nothing to compress here. But this 0 here, we can remove it. So instead of writing 0 db8, we can just write db8. Here, there's 3 zeros. So get rid of that, get rid of that, get rid of that. So we can write 1. Here we have 0A00. So that the trailing zeros we can't remove. So the leading 0, get rid of it. But the trailing zeros we have to write. Only the leading zeros. For example, if we take 2001, say we say db8 double colon 1. How do we know how many zeros are missing here? Because we can see this is one hexet. That's one hex. That's another hexet here. That's a second hexet. And there's another hexet here. So that's a third hexet. So how many are we missing? We meant to have 8, yeah? So since we see 3, there's 5 hexets are missing. 5 hexets of zeros. We can't have double colon twice because that creates ambiguity. For example, if I say 2001 colon colon db8 colon colon 1, well, that's not allowed. The reason why it's not allowed is because, okay, I can see 3 hexets. I can see that's 1, that's 2, that's 3. I can see 3 hexets. I know there should be 8 hexets, so 5 are missing. But I don't really know, are there 4 on this side, 4 zeros, 4 bunches of zeros in this side and 1 in this side. I don't know, maybe there's 3 in this side and 2 in this side. Or maybe there's 2 in this side and 3 in this side. See, I have an ambiguity there. 4 in this side. I don't know where it is. So for that reason, you can't use this twice. You have to use it once only. For example, 2001 0 db8 then double colon then 1. That is fine because I know, okay, that's 1 hexet, 2 hexet, 3 and 4. I'm missing 4, so I know here there's 4 hexets. Types of IPv6 addresses. So there is 3 types of IPv6. As we know, IPv6 does not have a broadcast. We have unicast, which is one-to-one addressing, a multicast, which is one-to-many addressing, and the new type of address called anycast. And anycast is, for example, IPv6 allows some addresses to be assigned, well, same address being assigned to 2 or more devices. And then when you try to access one of these devices, it's going to pick the closest to you. For example, say that one, just imagine one big server is assigned same address in Paris, same address in London. When you're in London, you're going to connect to the London server. When you are in Paris, you're going to connect to the same company or same type of server, but to the closest. So it's one to the closest. Unicast addresses, there's quite a few of them. So here we're going to go one by one. So for example, let's say we have here global unicast address. This, if you want to compare it to IPv4, this is like saying a public addresses, public IPv4 addresses. That's a global address. 2000::/3. So if you remember how many colons are missing, you see one hex that's, well, 7 are missing. It should be 8 in total. Then we have, if you remember, there's a type of in IPv4 are PPA addresses. So when you couldn't access the DHCP server, you assign yourself an address. So as long as you can communicate with each other, but those addresses are not routable. So same, we have a link local in IPv6 address, link local addresses. Every device, as soon as you enable IPv6 on the device, this device is going to assign itself a link local address. And all communication in the local network is going to happen through link local. Loopback addresses, it's : 1/128. So instead of reserving 17 million like in IPv4 for the same purpose, in IPv6 they reserve the first one only. Unspecified addresses, it's : 1/128. Well, that's a mistake. In unspecified addresses, it's just : just : When I don't know an IPv6 address and I was trying to assign myself an IPv6 address, I'll use unspecified address. Unique local addresses, these addresses are, if you want to compare them to IPv4, these are like private addresses. So private address. Not as much popular in IPv6 private addresses because there's so many addresses. We really don't use public. We only use public addresses. And then embedded IPv4 addresses : //80. Then we have in multicast, we have two types of multicast addresses: assigned multicast address and solicited node address. When we talk more about IPv6, like for example ARP, we see that we use this solicited node to find out the MAC address of a local IPv6 address. Thank you for watching section 4.2, Ethernet and Internet Protocols. We talked about IPv4 and IPv6. Please have a look at my other videos and don't forget to subscribe. Next video, 4.3, Connectivity Verification. Bye-bye.